All right, today we're diving into one of the most beautiful, elegant ideas in all of physics. It's a way to handle the absolute chaos of the subatomic world, not with pages of impossible equations, but with, well, with simple little drawings. This is the amazing story of Feynman diagrams. So just imagine the problem physicists were facing. When tiny particles, like electrons and photons, smash into each other, they don't just take one path. Oh no, in the quantum world, they do everything, literally everything, all at once. Trying to calculate the result of that kind of chaos, it seemed completely impossible. I mean, where would you even start?
You start by drawing pictures. Seriously, that was the revolutionary, almost mischievous solution that Richard Feynman came up with. He created this whole visual language that turned these mind-bending calculations into something you could actually doodle on a napkin. So let's see how he did it.
Okay, first, let's really set the stage here, because you need to appreciate just how massive this problem really was. The issue wasn't just that the math was, hard. It was that quantum mechanics itself seemed to throw up this giant impossible roadblock, the problem of infinity.
Here's the key thing you gotta remember. Quantum reality is basically just a giant soup of probabilities. To figure out the odds of a particle getting from point A to point B, you technically have to add up every single possible way it could have gotten there. And guess what? There are an infinite number of ways. This is the beast that Feynman's idea was designed to tame.
And that right there brings us to Feynman's big breakthrough. And this wasn't just some clever little trick. It was a fundamental shift in how physicists even thought about particles bumping into each other. It was a new tool that literally came in and saved the day.
In this quote, it really gets to the heart of the whole idea. Feynman just had this incredible knack for finding the simple, even joyful core of a super complex problem. His diagrams weren't just for number crunching, they were for understanding. He wanted to make physics feel intuitive and, fun.
So, what in the world is a Feynman diagram? Well, think of it like a perfect visual shorthand. Every line, every wiggle, every little meeting point in one of these drawings, it represents a specific, chunky piece of a very, very long and complicated formula. So you draw the picture, and you've basically written out the equation. The drawing itself is the calculation.
Now, to really have that aha moment, we're going to borrow a simplified little game from the source material. We're going to strip out all the confusing quantum physics for a minute and just play a simple game of connecting the dots. Okay, so here's the game. Super simple. Imagine you just have a bunch of dots on a page. Your only job is to connect them all up into pairs. Now, every line you draw has a value, a propagator. Let's just call it 1 over a for now. The final answer to the problem? It's just what you get when you add up the values for every single unique way you can possibly pair up those dots. That's it.
So let's try it with 4 dots. As you can see, there are exactly 3 ways to pair them up. No more, no less. Each one of these drawings is basically a little Feynman diagram. Now, since each drawing has 2 lines, 2 propagators, its value is 1a times 1a, which is just 1 over a squared. And since we have 3 of these possible drawings, our total answer is 3 over a squared. See? All of a sudden, a potentially complicated problem just becomes simple drawing and counting.
Okay, that's a fun game, but how does this connect to real-world physics? Well, to do that, we have to add one more ingredient to our little recipe, the forces, or what physicists call interactions between the particles. So on the left, that's the math for our simple dot game. This is for free particles that aren't interacting at all. It's a pretty clean formula. But on the right, that's the real world, where particles are pushing and pulling on each other. And to account for that, physicists have to add this new, much nastier interaction term into the mix. That little extra bit of math is what makes the whole thing so incredibly hard to solve. That new term, the one with the Greek letter lambda in it, that represents the force. And here's the absolute genius of the whole thing. If that force is weak, if lambda is a really small number, we don't have to solve the whole messy thing at once. We can use our diagrams to calculate the effect of that force piece by piece, as a series of tiny little corrections. It's a method called perturbation theory. So this method seems absolutely brilliant, right? We can now calculate anything just by drawing more and more of these little diagrams. But this leads to a super strange, really puzzling paradox. It turns out the answer is perfect, right up until the exact moment it becomes completely disastrously wrong. Just look at this table. It shows what happens as we keep adding more and more complex diagrams into our calculation. At first, it's incredible. The answer gets closer and closer and closer to the real value. By the 15th term, it's accurate to 3 decimal places. But then, something totally bizarre happens.
It actually starts getting worse. And then it just goes completely off the rails into utter nonsense, spitting out a value like negative 300,000. What is going on?
What we're looking at is something called an asymptotic series. The best analogy is like tuning an old radio. You turn the dial and you get closer and closer to the station. The signal gets crystal clear. And then if you turn it just a tiny bit more, you get nothing but loud static. This series gives us a ridiculously good approximation for a while, but if you keep adding terms, it eventually just flies off to infinity. So in a very strict mathematical sense, the method is wrong. It's broken.
So, here's the puzzle. We have this beautiful, intuitive idea that leads to a calculation that works better than we could have imagined and then fails so spectacularly. The math seems to be screaming at us that the whole approach is flawed. So what went wrong?
Absolutely nothing. Nothing went wrong. In fact, this seemingly broken, flawed method would go on to produce the single most accurate, most stunningly successful prediction in the entire history of science. This is where the story goes from cool to truly mind-blowing. See, the key is that in our actual universe, the strength of the electromagnetic force, that's the real-world version of our lambda, is a very, very small number. It's called the fine structure constant, or alpha, and it's tiny, about 1/137. Which means the force is pretty weak.
And because that force is so weak, it turns out we only need the first few terms, the first few, simplest diagrams, to get an unbelievably precise answer. This number you're looking at, this is the value for a property of the electron called its magnetic moment. It was predicted by the theory using Feynman diagrams. Now just try to remember the last few digits, 1, 6, 4, 3.
And this is the value that was measured in a laboratory experiment. Just look at it. Let that sink in. The numbers match. They match perfectly, digit for digit, all the way out to the 10th decimal place. It is an absolutely staggering, unbelievable agreement between theory and reality.
This just shows the ridiculous power of Feynman's idea. That whole weird paradox of the wrong series? Well, in practice, it just doesn't matter, because the universe was kind to us. The force is weak enough that those first few super accurate terms are all we need to describe reality. This isn't just a win. It is the most precisely tested prediction in all of science, period.
And so we end up with this really deep, kind of haunting thought. A method that's built on a mathematical series that is technically broken, that is technically wrong, ends up describing our physical world with the precision that we've never, ever matched. So it makes you wonder, right? What does that tell us about the real connection between our neat and tidy mathematical laws and the messy, fundamental nature of reality itself?